Hi students, now we are going to derive the expressions for the molar specific heat capacities of a gas Cp and Cv using law of equipartition of energy, which is very important for competitive exam problems. Now for that, first I will consider a monoatomic gas. Monoatomic gas such as helium, neon and argon. Now we have studied the average kinetic energy per degree of freedom is half kT. So for 1 degree of freedom, the average kinetic energy is half kT. Now for a monatomic gas molecule, the number of degrees of freedom are equal to what? 3. So the average kinetic energy of one molecule must be equal to 3 times half kT. So that is equal to 3 by 2 kT. So 3 by 2 kT is the average kinetic energy of one molecule of a monatomic gas. Therefore, average kinetic energy for 1 mole. So what is the number of atoms in 1 mole of any gas we have studied according to Avogadro's hypothesis? It is equal to the Avogadro number Na. Therefore, average kinetic energy per mole U must be equal to Avogadro number multiplied by the average kinetic energy per molecule. And the product of this Avogadro number and Boltzmann constant I have separated. So U equal to 3 by 2 into Na into K into T. And this product Na into K only is equal to what? The universal gas constant R. Therefore, this U is now equal to 3 by 2 RT. And this is the first equation required. Okay. Now, after this, we want to derive expressions for Cv first and then followed by Cp. So, specific heat capacity, that is specific heat capacity at the constant volume. So, by keeping the volume as constant, we find Cv first. Cv is equal to the rate of change of the internal energy du divided by dt. So this is equal to d by dt of, in place of u, I have to substitute 3 by 2 r into t. So while differentiating, the constant shall be taken out. So now Cv is equal to this 3 by 2 r, 3 by 2 r into d by dt of t is equal to 1. So Cv will remain as what is 3 by 2 r into 1, that is 3 by 2 r itself. So this is very important information for a monatomic gas molecule. The specific heat capacity at constant volume Cv is equal to 3 by 2 times r. Okay, now from Mayer's relation, we have derived a Mayer's relation in the class. What is the relation? Cp minus Cv is equal to R. So Cp minus Cv is equal to R and Cp is equal to Cv plus R. So this is equal to 3 by 2 R. I am going to substitute for Cv. Okay, so this is now equal to, okay, this is a 3 by 2 r plus r. Now if you take LCM, this will become 3r plus 2r whole divided by 2. Therefore, Cp is now equal to 5 by 2r. 5r by 2. So this is equal to 5 by 2r. And this is our equation number 3. So now after this, the ratio of Cp and Cv is equal to the adiabatic constant. That also we are going to determine now. So the adiabatic exponent, adiabatic constant or adiabatic exponent is gamma. Gamma is equal to Cp divided by Cv. So in place of Cp, in the numerator 5 by 2 r. So this is 5 by 2 times r divided by Cv is 3 by 2 times r. So this 3 by 2 r So this R get cancelled and the common factor 2 also get cancelled. So after cancelling this constants, this is equal to 5 by 3, and 5 by 3 if you divide means it must be around 1.666 recurring, is it not? So this is equal to 1.666, like that it will be recurring. So I am rounding off these digits to, so gamma is now equal to 1.67. This is the final value required here. So this is equation 4, step number 4. So in this type of derivation, always whether it is monatomic or diatomic or triatomic at different temperatures, first we start with the average kinetic energy per degree of freedom. Then for one molecule, then for Avogadro number of molecules, that is 1 mole, and then differentiating we get CV, followed by Mayer's relation, we determine Cp, and we take the ratio and get what the value of gamma. I hope you must have understood well. Fine.